you all, Darrell Lee Berry Jr. back with some more quantum reading. So I plan on continuing through chapter 7, section 2 of uh, Griffiths. So it's pretty much the standard textbook, at least at my university, for quantum 1 and 2, perhaps even quantum 3, but I won't be taking quantum 3. So looking at what we have here, we're starting in the middle of 7.2.1, if I recall, dealing with degenerate uh, perturbation theory. So basically, the idea of applying perturbation theory to a quantum state where you're dealing with degenerate energy states, and what do we do with that? So I left off on this derivation, where we're basically finding the uh, eigenvalue for the sort of the matrix state comprised of the expectation value of the uh, perturb Hermitian operator. And we're continuing with that. So let's see what we have. So this is an example 7 point, well, not an example, but the process on 7.31. And basically I remembered the linear algebra process of subtracting the uh, eigenvalue, multiplying it times the identity matrix, setting it equal to 0 and taking the determinant. So I'm working that out right now. We'll see what we get. This is how they got line 7.31. It's actually equals 0. I'm basically doing the linear algebra method of finding the eigenvector. So multiplying the um, identity matrix times E1 makes E1 into a matrix. So then we have the next line, and I'll actually write this out. It's the W matrix. That's E multiplied by the identity matrix. Use this with the notation for the determinant. Let's put another bracket. Technically, this is 7.31. I'm seeing what it was too early. So what I have to do now is take the determinant of this, and we fulfill the linear algebra process outlined there. See if I could adjust my mic a bit. We want to take the determinant of WAA minus E1, WBA, WAB, and WBB minus E1, and set that equal to 0. So we have, just multiplied that out, and looks like they made the last line a square. Suppose what they're saying is WAA, or at least WAB, equals the complex conjugate of WBA. So that's how we get WAA squared minus W, and they called it AB, the magnitude of AB, and minus WAA E1 minus WBB E1 equals 0. And I left off a term. The first one, WAA squared. The last one plus E1 squared. Oh, that's what I did. WAA, WBB plus, right, there we go. As the professor made this into a quadratic equation, um, all in the quadratic. Getting an error. A moment here. Let me see if something is wrong with the stream. There's an error issue with the keyframes. All right, well, I'll have to fix that next time. So if anybody's having an issue with with any buffering, let me know. Let me try to find something here. I don't see how the professor made a quadratic out of this either. Get a sip of water. I'll be right back. Right. So this is something I'll ask my professor about. Um, the exact way he made a quadratic equation out of this. Looking at the wrong variable, maybe which it is. I see. So we have we're solving for E. So if I was to rewrite this, I was thinking about trying to solve for W. So we have E1 squared from the outer. Then we have a minus WAA minus, I'll go ahead and do, yeah, minus WAA plus WBB E1 minus plus WAA WBB minus the magnitude of WAB. All right. So now it makes sense if we solve for the E as a variable. Interesting. So I guess the eigen, right? So that means that alpha and beta are the vectors, and E, I guess, is the eigenvalues. I need to refresh myself on linear algebra. And this consolidates that unless we end up with quadratic equation. We have E1 squared, E1, and then nothing equals 0. All right, so now we're on the same page. So I won't go through the process of solving the quadratic as long as we can see what it is. When you go through the process of solving it, then again, the quadratic equation is x equals negative b plus or minus square root of b squared minus 4ac all over 2a. In this case, x equals e1. And this would be a, this would be b, and this would be c. So a is actually 1. C is that entire thing. B is that entire thing with a minus sign in front. And if we solve the quadratic with that, we have E1 plus or minus equals 1/2 WAA plus WBB plus or minus square root of WAA minus WBB squared plus 4 the magnitude of WAB squared. 7.33. This is the fundamental result of degenerate perturbation theory. The two roots correspond to the two perturbed energies. All right, so we're finding the energies of these perturbed states. To give us an example, I think is worth doing. To start by calculating the matrix elements. So apparently this equation is going to be very important. This is equation 7.28. I don't recall example 7.2. The first thing to do is get all of the matrix elements. So W A equals to the formula. That's going to be It's an X and Y. I forgot because we have a two-dimensional system with a perturbation. It's going to be two derivatives. Hmm. Somewhere in here I must have missed when they utilize epsilon to refer to the uh, curve potential. So I'll just make a note of this for now. Basically, we're taking the uh, it seems that H prime acting on psi AXY seems to equal epsilon m omega squared x. In which case, we can take out the epsilon m omega squared and we still end up with omega naught x squared. I notice that removes the a as well. It's like they broke them into two integrals. WAA, WBE equals zero since they're odd functions. See what WAB does. By the way, it's xy. Just the function is xy. So h prime acting on b naught. I have to ask why this is the case. We're gonna remove the a, and it's just something squared. No, this is different. You want us to recall the case in 270 from chapter 2, which I showed you didn't recall. X equals that from equation 2.70. And y equals the same thing. We have the same thing. These two are equal. We can Put these on either side. Seems to be what we have here. Need to recall this process here. I'll ask about to look into later. I believe that's the case with that. This becomes this. This is going to equal 1. So this is the same thing squared over the full range. WAA. So W equals WAA, WAB, WBA, WBB. So this equals 0, 0. E H bar omega over 2. E H bar omega over 2. And it is extracted that out to make it simplified. Eigenvectors normalized R1 over square root of 2, 1, 1 over square root of 2, negative 1, 1. These eigenvectors tell us which linear combination of the good states. eigenvalues of the matrix W are those. That WAB equals 0 in equation 730, and the two eigenvectors are from the previous formula. Possibly would obtain using non-degenerate perturbation theory. We have simply been lucky. If states YA0 and YB0 are already the good linear combinations, obviously it would be greatly to our advantage. We can somehow guess the good states right from the start. Then we could go ahead and use non-degenerate perturbation theory. As it turns out, we can very often do this by exploiting the theorem in the following section. Right? We'll go to this. And let me check something real fast. Let's go through this and see what we get. Theorem is Hermitian, commutes H naught and H prime. F dot AO and psi BO, the degenerate eigenfunctions of HO. Also eigenfunctions of A. distinct eigenvalues. A psi A0 equals mu psi A0. A psi B0 equals mu psi B0, and mu equals not. Then psi 0A and psi 0B are states to use in perturbation theory. Since H equals H naught plus, right? This is saying that the perturbed Hermitian is the unperturbed Hermitian plus whatever relevant order of the perturbed Hermitian, and A mute, as it said, A commutes either, so it commutes both. Take simultaneous eigenstates gamma lambda, where H lambda psi gamma lambda equals E lambda psi gamma lambda, and A psi gamma lambda equals gamma psi gamma lambda. All right, let's look at this. This is the perturbation plus a default Hermitian has given us the whatever order of the new Hermitian commutes with A. So we get simultaneous eigenstates psi gamma lambda, where H lambda, H, the combined Hermitian acting on the eigenstate, gives the energy as the eigenstate. So this is what we're used to. Then we have A acting on the eigenstate, gives us gamma as its eigenstate. So E is the eigenvalue of psi gamma lambda, with h lambda acting on it, and gamma is the eigenvalue of the same eigenstate with A acting on it. And A is a Hermitian operator as well. Okay? So A being Hermitian means that psi A naught A psi gamma lambda equals A psi A naught psi gamma lambda. This makes sense because this is Hermitian. We could move it around how we like. And gamma psi A psi gamma lambda equal complex conjugate of u psi A psi gamma lambda. This is 7.37. And gamma minus mu psi 0A psi gamma lambda equals 0. Right? So this makes sense from this. First line getting there a bit. So A gives gamma. A acting on that state can give gamma. So it looks like these two are equal. A acting on psi gamma lambda gives gamma, psi gamma lambda as we see here. And now gamma is just a variable, so it can be just pulled out to the front. I don't see where they're getting mu from, but I suppose they're just throwing that in as something they're building upon. And this is 7.38. Make use of the fact that mu is real. This holds true for any value lambda, and taking a limit as lambda goes to 0, we have I just covered limits on my other channel recently. Equals 0 if gamma equals not mu, and psi b 0, psi gamma 0 equals 0 if psi equals not mu. So if psi equals not mu, it equals 0. wrote that differently. Now the good states are linear combinations of those two. Well, it follows that either gamma equals mu, in which case B equals 0, and the good state is simply psi A, or gamma equals, and the good state is that. Okay, I miswrote this. That's why I was missing that part. So they're relating B to that and A to that. So if gamma equals mu, B equals 0. Gamma equals mu. B equals 0. Gamma equals mu is not B. So B is 0. And psi gamma 0 equals alpha psi A0. And if gamma equals that, if it doesn't equal that, so A equals 0, psi gamma 0 equals B gamma B0. So I get that concept. Basically, instead of using the full perturbation theory, we could just use these good states and circumvent having to actually apply perturbation theory. In the case, we could identify the good state, so apparently is more applicable than um, regular person perturbation theory. Symmetries are associated with symmetries, and those symmetries let us know about degenerate state. So symmetries associated with operators that commute with H. So now we have an example and some problems. Let's read through this example here. Example 7.4. Find an operator A that satisfies the requirements of the preceding theorem to construct the good states in examples 7.2 and 7.3. Conclusion: the perturbation H prime has less symmetry than HO. HO has continuous rational symmetry, rotational symmetry, but H equals H naught plus H plus is only invariant under rotation by integer multiples of pi. For A, take the operator R pi that rotates the function counterclockwise by an angle pi. Acting on our state psi A and psi B, we have R pi, so we're rotating it. Psi 0 8xy equals YA0 negative x negative y equals negative psi 0xy R pi psi B0 is R B0 negative x negative y or negative B, right? This is no good. We need an operator with distinct eigenvalues. How about the operator that interchanges x and y? This is the reflection about the 45-degree diagonal of the well, called the operator D. D commutes with both h prime and h. Oh, since they are unchanged when you switch x and y. Now, so now eigenvalues are the same, I guess. So the general eigenstates are not eigenstates of D, but we can construct linear combinations that are. Then plus minus. These are good states since they're eigenstates of operator D with distinct eigenvalues plus minus negative plus minus 1, and D commutes with both H0 and H prime. Moreover, if you are faced with degenerate states, look around for some Hermitian operator A that commutes with H naught and H prime. Pick as your unperturbed states ones that are simultaneous eigenfunctions of H naught and A with distinct eigenvalues, and use ordinary first order perturbation theory. If you can't find such an operator, you have to resort to equation 7.33, but in practice, this is seldom necessary. Right? Can't say I understand this section so well, but we'll see. So what I may need to do is go back to the first section and try to read it all together. That'll make for a long video, but seems like really going through each of these examples is going to be a big help. So perturbation theory started off pretty simple, but it's getting pretty complicated. All right. So thanks everybody who watched. Make sure you like, subscribe if you haven't. I'll probably be back. I'll look at my calendar and see what day. I think I will do that and come and read all these sections in order. Um, and see if that might help. But it might not be until Thursday night. So we'll see. See you all next time.